maybe you know that I'm working through my chapter summaries for matter and interactions. I'm on chapter 17, so if this is the book, I'll describe the book down below. Wiley, Chabay and Sherwood, Matter and Interactions, the best physics book ever, and this is chapter 17. So again, this is just a summary. Read the book. A lot of great stuff there. Let's just start off with a demo, right? I can do a demo. I have here a compass. Maybe you've never seen one of these before. That doesn't look like it's pointing the right way. There you go. So this is a magnetic compass. It's still not pointing the right way. That's fine. I'm going to bring a magnet near it. And you can see that I can move. There's my magnet. I can, this points in the direction of the net magnetic field. Okay. Now, that's not the cool part. The cool part is, what if I take a battery with magnets on it, but it doesn't really matter. That's just so I can connect this. And I'm going to hold the wire straight over that. I'm going to take away this magnet. Okay. And now I'm going to touch the battery wire and turn on the current, and let's see what happens. So you can see that an electric current also makes a magnetic field. And that's really the whole point of this chapter. How do we make magnetic fields? So we've already done this. Let me just write it down here just as a review. We have E equals 1 over 4 pi epsilon naught Q over the magnitude of R squared R hat, right? And so just as a review, if I have some charge right here, we'll call this RQ. That's a vector. And then I want to find the electric field right here. I need to find R observation. And this is the vector R. And that would be E. We did that, right? We did that a couple times, so I don't want to go over that. Well, we're going to create the same equation, or an equation for the magnetic field due to a moving charge. And that's the first thing. Let's just review. We talked about drift velocity. Remember, if you have a electric field in the interior of a metal, you can get moving charges. So let me just show you there's a couple great demos on the WebVPython GlowScript page, and they have all these demos. Let's look at this one right here, and I'll put a link to this because they're all here and they're great. They're written in Python too, which is great. So this is a model of a metal with an electric field. So if I have an electric field inside that metal, and I know we said you can't have electric fields inside a metal. Well, you can, okay? If it's in static equilibrium, you can't, right? Because these charges would move if it's in a solid piece and build up on one side and make the electric field zero. But here, for some reason, there's no end over here. There's no end over there. If I have a constant electric field, these negative charges are able to move with an apparent constant velocity, but it's not. They actually speed up and slow down, so we have some average drift velocity. But it's this moving charges in that wire that create that magnetic field, and that's what we want to find out how to model. Okay, so with that, we're going to come back to this in just a second. So with that, we have the equation for the electric field. Suppose that I have a charge Q, and it's moving with the velocity V, and it's at some observation location. It doesn't really matter. I'll call it RQ. And I want to find, let's put it over here, the observation location down here is RO. And I want to find this vector, R. And remember, just like before, R is RO minus RQ. So you don't have to have the charge at the origin. This is the way to adjust for that. But I do need the velocity vector. I'm going to write it down, and then we'll talk about something. The magnetic field B is equal to mu naught over 4 pi QV cross R hat over the magnitude of R squared. And remember, R hat is a unit vector, and we can write R hat as R hat is R over R magnitude. If I substitute that in, I get a slightly different version, mu naught over 4 pi QV cross R over R cubed. Both of those are fine. You use the one that makes you happy. So we have a couple things here. First, what's this term? This is our magnetic constant, mu naught over 4 pi is equal to 10 to the negative 7th. And the units on that, I always forget. Let me look them up. Tesla, meters squared per coulomb, meters per second. And T is Tesla, not the car. And that's the unit for magnetic field, which we represent with the vector B. Okay. Now, we do have to address this cross product, and you may have seen that in your introductory physics course the first semester when you're dealing with angular momentum and torque, but maybe you forgot. So let's just say I have the vector A as AX, AY, AZ, and the vector B as BX, BY, BZ. Then A cross B is a little difficult to write, but I'm going to write it, and I'm going to use my formula, so don't worry about this. We can write this as the determinant of the matrix X hat, Y hat, Z hat, AX, AY, AZ. I don't expect you to, my students, I do not expect to memorize this. BX, BY, BZ. And now I just expand about that top row. So I get the X component is going to be AY, BZ minus AZ, BY. The Y component, it actually gets a negative 1 in front of it, so we're going to do this way. It's going to be AZ, BX minus AX, BZ. And I'm running out of room, so I'll put a comma there. And the last row we expand is going to be AX, BY, Y minus AY, BX, X. And that looks crazy, and it's a little crazy. There's actually another formula for this. The magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between those two. Okay, let me jump over to something really quick. I do want to remind you A dot B is equal to AX BX plus AY BY plus AZ BZ is the dot product. Notice here that we get a scalar answer. Here we get a vector answer. So this is often called the scalar product, and this is called the vector product. But the important thing is that this gives you a vector, and you can calculate the direction using these components. But a lot of times we're going to use our right-hand rule, and this is where that right-hand rule comes from. Let's jump back over here to the computer, and oh, look at this. Cross product right there. I'm going to click that one. No, I'm not in the wrong spot. This one. Very useful. This shows the cross product between these vectors, and you can rotate the whole thing around, right? So here it has, it's yellow is red cross green. So here's red. I can grab that. I'm grabbing green. Can you grab red? No. Okay. So notice that as the angle between them gets very small, sine of theta is very small, so it gets 0. The yellow is the resultant. And it's maximum when they're perpendicular, and then it gets smaller. And so if I change the length of this, you can see that. But what I want to focus on is the right-hand rule. So this resultant vector, and this is going to take some practice, notice that the green and the red are in the plane of this grid. The yellow is perpendicular to that. So the result of a cross product has to be perpendicular to both A and B. And there's no way to do that in 2 dimensions. It has to be in 3 dimensions. So there are only 2 vectors that's perpendicular to both red and green. Let me rotate this around so it goes on the other side. This is red cross green. So there's this vector coming out this way, and you could do one on this side. Both of those are perpendicular to both of those vectors. How do you pick? Well, this is my right hand. So use the right hand rule. And you got to do it this way. So the right hand rule says that if you let the fingers of your right hand, okay, it doesn't look like my right hand, but the screen's backwards. If you let the fingers of your right hand cross the first vector, red, and then the second vector, green, your thumb will point in the direction of the resultant. So that tells you which of those two to check. They also have, you can do it like this, red, green, yellow. There's a lot of different versions of that, and it's going to take a lot of practice. So we'll talk about that later. Yeah, that's good enough for now. Okay, so let's go back to this magnetic field. So where did we go? Oh, right here. So this is the magnetic field. Notice that we're doing the cross product between V and R. So the magnetic field B is going to be perpendicular to both QV and to R. So in this case, let's just draw that direction. If I want to find the magnetic field down here, and it does matter which if it's positive or negative charge, right? So positive QV is that way, R is this way. So if I do, there's only two vectors that are perpendicular to both of those. So here are my two vectors, that one and that one. And I want to do QV cross R, which is not R cross QV. The two vectors that are perpendicular are this way, coming out of the paper, and then going into the paper, right? Those are the two. How do we pick? Right-hand rule. So if I let my fingers cross this way, they cross this vector in that way, and then I get this as B. So we're going to use this symbol right here to represent a vector going into the paper. It's an arrow, and you're looking at the feathers. If you had an arrow like this, that's an arrow coming out of the paper. Okay. So, but this case, it's going into the paper. This is going to take a lot of practice. So it's a 3D thing. Just don't let yourself get too hung up on that. I do want to say one thing though, since we're dealing with velocity, and this is an interesting point. Imagine I have a point charge right there, and it makes an electric field. Well, if it's not moving, it doesn't make a magnetic field. It just makes an electric field. But what if you're moving? If you're moving, the observation is moving this way. It looks like that's moving that way. So you could have two people, one stationary with respect to the charge and one moving, and they would disagree about the strength of the magnetic field. The magnetic field is relative. So, we talk about absolute and relative, and this is one of those first cases where it depends on whether you're moving or not. Now, the result we'll probably agree on, but the magnetic field we do not have to agree on. Okay, let's talk about current. And I'm not going to solve these problems for you. We're setting them up, right? We're setting it as a summary. So remember, we're going to define the electron current as, we'll call this electron current. I is in a V. That's not an arrow. I didn't mean to do that. So N is the charge carrier density. A is the cross-sectional area. I'll just put cross area. And then V bar is the drift velocity. So this is really the flow rate. I is the flow rate. We call this the electron current, but it's the flow rate. And it's not really flow rate, but flow rate of charges. It's the charge per second, how that flow past a point. And just check, right? N is just a number per volume. And that's an area. So that's a meter squared, and then I have meters per second. So I get 1 over a second. So it is that's charges. So it's charges per second. So it is the units for the electron current. No, this is the electron current. This is the number of electrons. This is electrons per second. And so you can see here that if I have, a thick wire and a thin wire, then they can have the same drift velocity, so the electrons are moving the same speed in both of these. But since this one's larger, there's going to be more of those charges moving per second. And that gives us to the conventional current, I. We'll write that as Q in a drift velocity. So this is, if I multiply it by the value of the charge carriers, which is probably an electron, we don't really know, but let's just say the charge is an electron, then this gives us coulombs per second. Coulomb per second, which is equal to an amp. That's what we're going to call current. So we have lowercase I as the charges per second, and this is the charge per second. So the electrons per second. Now, we already said that the drift velocity inside of a metal depends on the applied electric field. So drift velocity is U times E. So the electron mobility times the value of the electric field. So if we put all that together, we get I equals Q in a U E. And it looks bad, but it's not really bad, and it's all fine. And this is the charge, the conventional current. Now, we describe conventional current as the flow, the direction that a positive charge would be moving, and in a lot of cases we can't tell the difference between a positive moving that way or a negative moving that way, but there is a way, we'll learn it later, it's called the Hall effect, but we just assume it's positive charges moving, even though it's usually not. Okay, what next? Next, we have, what if I don't have a moving charge, but I have a current? Well, a current is moving charge. So how do I find the magnetic field due to a long wire? Well, if I have a short wire, say I have a really short wire right here. It has a length delta L, and that's a vector because it shows the direction that the wire is. And there's a current in there. So we have I delta L. It turns out that I delta L is the same as QV. Has the same units and everything. So a single moving charge with a velocity or a current and a length of wire, right? And I don't care about how wide that is because I've already taken that into account with the current. So this is the number of coulombs per second times the length gives me the same units. So we can use this as long as it's short as that. We can't use it if it's long because then they have different contributions, and I'll show you that in a second. So, but I can get this, delta B is mu naught over 4 pi I delta L vector cross R over the magnitude of R cubed. Or you could write that R hat over R squared, whatever you want. So it looks the same, but this is just a contribution of a short piece of a wire. Now what if I have a long wire? And I want to find the magnetic field over here a distance R away. Well, what we do is just take the contribution of the magnetic field due to this piece right there, plus this piece, and so forth, just like we did with the electric fields. And in this case, I'll do this result later and derive it for you, but you get this. B, the magnitude, first of all, it's going to, if the current is this way, the magnetic field's going into the board, and we get the magnitude of mu naught over 4 pi, that's a pi, I times L over R times the square root of R squared plus L over 2 squared. And if you're really close to it, that's approximately equal to mu naught over 4 pi 2I over R. And again, don't worry about that. We're going to derive it later. And I'm going to show you how to do this with an animation from the great demo site. We're going to go back to the demo site. B wire with R. That's what I want. Right there. So this shows a wire broken into finite segments. We're going to do it eventually as an integral by letting the segment size go to 0. But if I want to take that little piece right there and find the magnetic field, where am I? Right at this point, then I just keep doing that and adding up the magnetic field due to all these pieces. And you'll notice that it's perpendicular to the wire, right? And it's perpendicular to the current. And then I keep doing that for every little piece, and let's just go all the way. I think it just jumps to the end. There it goes. Okay, so now it's doing it, and we can see what the shape of that looks like. Notice that this is inherently different than the electric field due to a charge. An electric field due to a charge, the electric field points away from positive charges and towards negative charges. And this is making like a circular pattern around the wire. It doesn't start or end anywhere, right? So it's a very different type of field pattern around this wire. And you kind of can get a feel for this in this animation. But this is what we're picturing when we think about magnetic fields due to wires. They kind of like curl around it. You can put the thumb in the direction of the current and your fingers show the direction the magnetic field curls around. And so what they're doing also is as you get further away, the strength of the magnetic field decreases. So this is a great picture right here. I mean, this is just like art and physics and everything and Python, and I don't know, I just want to look at this forever because it's just awesome. So well done. I love it. I love it. Isn't that great? Okay, so this has a magnetic field coming out of the page so that the current's coming out of the page, so the magnetic field goes this way. If it was going into the page, the arrows would be in the opposite direction. Okay, let's go back over here. Let's do the magnetic field due to a loop right here. One step at a time again. So here, what if we have a loop of current, a current going around in a circle? Well, we can do the same thing here, taking the magnetic field due to all these contributions and adding them up, and we get that. And then they do it at a whole bunch of different locations. I do want to show you something important. So they're going all the way around the ring and find these magnetic fields. This is a great animation. And looking, I don't know if you'll notice this, but this should look familiar. Wait, that one's wrong. Oh, it's yeah, that's right. Okay. Almost done. Okay. So here is the magnetic field due to this loop of wire. And if you remember from before, this looks like the electric field, the same shape of the pattern as the electric field due to a dipole. That's kind of a big deal. Okay, so let's go back to the paper and talk about the magnetic field due to a dipole. I mean, a loop. So I'm not going to derive it, but the magnetic field due to a loop is equal to mu naught over 4 pi 2 pi r squared I over, let's put this as z squared plus r squared to the 3/2. So here, this is the loop right there, and that's the value z. Now, if the loop's really small, we can actually write this as mu naught over 4 pi 2 pi r squared I over r cubed. And that's really important. We didn't cancel the pi's because pi r squared is the area of that loop. So we can actually write this as mu naught over 2 pi 2 mu over r cubed, where mu is NIA. So that's the number of loops, the current in the loop, and the area of the loop. And yes, this is the magnetic dipole moment, just like before. We had an electric dipole moment. This is the magnetic dipole moment. The equation looks the same as long as you're far enough away from the ring or the ring small. That's kind of a big deal. Okay. So let's talk about a couple other things. Let's talk about the Earth just because it's fun. So here's the Earth. Here's Antarctica. There's poles, right? That's the South Pole. And that's the North Pole. So north, south. And this is bears, no bears. So just if you may not know, Arctic means bears. There are bears at the North Pole. There are polar bears up there. They're very dangerous. And this is Antarctic, which means no bears. There are no bears down there. I don't know why. That's the way it is. And that's what those words mean. But the more important thing is if I have a compass and it points north, it points that direction because it's interacting with the south magnetic pole up there. So this is the south magnetic pole and this is the north magnetic pole. So those two are flipped. The next important thing I want to mention because it comes up, monopoles. So remember, if I have a positive charge, it makes an electric field like this. If I have a dipole, it makes this field like, I'm going to just draw the lines like that. And so we can do it that way with electric charges. Well, we have a way to make this with a magnetic field, with a loop. Do we have a way to make this with a magnetic field? No, not that we know of. I mean, mathematically it would work, but that would be a single magnetic charge. We think of magnets as having a north and a south pole, just like a dipole has a positive and negative charge. But it turns out that we never see a single magnetic charge by itself. It would be called a magnetic monopole. It doesn't mean they don't exist. We just haven't seen them. Okay, I think that's good for chapter 17. I'm definitely going to do that derivation of the magnetic field due to a loop and due to a wire because it'll be fun. But that's that. Read the book. The book's awesome, and I'll talk to you later.